So we've talked about two of the several rules of logarithm and exponent properties. Let's bring in three more here: the product rule, the quotient rule, and the power rule. I like to call these the accordion rules because it expands and contracts. Have you ever seen someone play an accordion? It expands and contracts. It's kind of a wheezing instrument. And you pull it apart, it gets bigger, so the air comes into it, and then you push it back together so that the air rushes out of it, and you get to make music that way. My father played the accordion growing up, and when my brother and I would misbehave, we would get like 10 minutes with the accordion. Not us playing it, but listening to my father play it, and he wasn't a very good player of the accordion. And it was kind of horrible to listen to. So I have fond memories and horrible memories of the accordion all at the same time. So maybe that's why I thought of the accordion when it came to the product rule, the quotient rule, and the power rule. So one way expands it. If you look from left to right, it goes from being one log to being multiple logs. And another way it contracts. It goes from being multiple logs to being just one log. And the same for the quotient rule. Goes from one log to multiple logs. And the power rule, it stays one log, but it gives a multiplying factor to it. All right. Now these rules work both ways. Okay. And when you multiply things, we can turn it into an addition. When we divide things in a log, we can turn it into a subtraction instead. And then there's the power rule. So each of these rules we're now going to use. Now the power rule, let's take that as a special note here, because power rule, while it doesn't expand per se, it does add a multiplying factor here. And it is one of the most powerful rules. But in the power rule, it says that, hey, if you've got an exponent to a value that's part of your log, you can take that value instead and bring it in front of the logarithm itself. When we go to solve things that have exponents, this is going to be one of the great things that we use to do so. All right, so let's take a look at example 10 on page 336. Let's go ahead and get our accordion out of here so we have some space to work from. On page 336, it says rewriting logarithms. It says to rewrite each of the following expressions as a sum, difference, or product of logarithms and to simplify if possible. So in this way, we're going to expand these out. It's going to go from being one log to being multiple logs. All right, so part A, we have log base 4 of 5 times x minus 7. So what I see going on here is a multiplication. I see 5 times the quantity that is x minus 7. And so with the product rule here, we can take one log and turn it into two logs with an addition in between here. So let's put a little arrow here, and we're going to say this is the same as saying log base 4 of 5 plus log base 4 of x minus 7. And now it's turned into two logs. There's a reason sometimes we want to turn things into two logs versus one. There's a reason sometimes we want to consolidate logs down from two logs to one. But that's coming. Those reasons are coming. So just bear with me here. We'll get to that in a little bit. But let's first just focus in on the process of expansion and contraction. All right, part B of this example, we have the natural log. We haven't seen one of those just yet, other than us talking about definitions, of e squared times e plus 3. They've given us some fun parentheses to use in our writing on this particular one. But the same thing happens from the last one. It doesn't matter that it's a log base 4 and this is a log base e. This is what we call natural log, right, from our part B of definition of log. The same thing that we're seeing in B, we saw in A. We see a multiplication, in this case, e squared times e plus 3. And so we're going to turn it into two different logs here. So we're going to turn it into the natural log of e squared plus the natural log of e plus 3. Now, the last one, when we did that, there was nothing more to do, and so we stopped. But here we have one more thing that we can do, actually a couple more things. First, this 2 can be brought into the front of the log per the power rule here, number 5. So let's do that. We can say that this becomes 2 ln e plus ln of e plus 3. All right, looking pretty good here. And there's one more thing we can do to this, which is the ln e is a very special value. Because what ln e is saying log base e of e equals something. Anytime we see ln e, it's actually 1. It's not really a rule that we've added so far over here, but we could add it right here if we really wanted to. We could say that, what, ln of e equals 1. Because ln e equals 1 is just an actual rule. And so that means that we're going to have here is 2 times 1 plus ln of e plus 3. We'll just call this one 2 plus ln of e plus 3. So it took a little bit of work to simplify this down a little bit once we did that. But in the end, that got us to the right answer. And we found a truism along the way here, right? That ln of e equals 1 as well. All right, moving into part C of this example, we have the log. So it's log base 10, even though we're not going to say that. And it's a division that's happening. It's x minus 8 divided by x. So it's log base 10, or just log as we like to say, of x minus 8 divided by x. And this is a division that we can take advantage of. And so we're going to use the quotient rule over here that says, hey, if you've got a division happening as an m divided by n, then you turn it into a subtraction. And so that's what we're going to do. We're going to call this the log of our numerator as in x minus 8 minus the log of our denominator, which is just x. And there's no more simplifying we can do here. Certainly if there was, we would want to take advantage of it. But there isn't, and so we'll just leave it as that. Part D looks like a straight up power rule here. It has log base 4 of y to the 6th power, which means that we get to take advantage of the power rule again. And all the power rule says that if there is a power to the value of your log, you take that power in front. And so for us, that means that 6 comes in front, and the rest stays exactly the same, sans the 6. So in other words, 6 times log base 4 of y now, not to the power of 6, because that 6 came in front. All right, we have one more to do. Let's see if we can squeeze it in over here to the far left, part E on this one. We had the natural log of 1 over x to the 5. Once again, a quotient rule for us to take care of because we have a division that's happening here. So that means we're going to have the natural log of 1 minus the natural log of x to the 5th. For this one, we do get to move the 5 to a space. So let's take care of that. So we have the natural log of 1 minus 5 times the natural log of x. Looks pretty good here, except how do we get to the natural log of 1 or even the log of 1? Because remember what it's saying. It's saying the power to our base. So again, natural log, our base is e. So e to some power equals 1. Well, there's only one power that no matter what the base is will always give you 1, and that's 0. So essentially the natural log of 1 or even the log of 1 is really 0. And so we're going to have 0 minus 5 times natural log of x, and we really don't need that 0. So the best way to write this is just to say minus 5 natural log of x. And we found yet another truism here, which is that any log base to 1 is always the same thing as 0. So that's another great thing that we just found as part of our work here on example 10.